everyone, depending on where you're calling in from, and welcome to this GTMA-sponsored webinar on collecting the road of tomorrow. We have a couple of very interesting topics that we're going to be discussing today with some very interesting speakers. We're going to first discuss how we're going to be collecting data as it relates to and describing the roads of Utah, and Mr. Ray Mandli will talk about that. Then we're going to be talking about how that data can be used and related to safety system research and autonomous vehicle research by a couple of other speakers. Our speakers today are Ray Mandli, who is the president of Manley Communications, and Ray is going to be doing the Utah data collection, and he'll be describing that first and the map that's going to be created from it. Jim McBride is going to talk about the implementation of that map and how it might be used for advancing research on things like car safety systems and other types of applications. And John Leonard is going to talk more specifically as it relates to that map and autonomous vehicle navigation. So we're going to be touching on a number of different subjects today. And before we move on, I wanted to kind of maybe set the stage for the webinar for those who may not be as into these topics as we all are. I know it's easy to assume a level of knowledge here, and I wanted to kind of set a baseline for what it is we're going to be talking about. We're going to be talking about maps, and when we think about a map, you know, it's not the map that you might pull up inside your car when you're looking to navigate to Cleveland. It's not the Google map that pops up when you're trying to navigate down to McDonald's. We're talking about maps that are collected mobily using vehicles equipped with some pretty sophisticated equipment. And for example, you'll see, if any of you have seen, for example, the Google cars, the self-driving cars driving around, you can see there's a spinning LiDAR on top, there's some other sensors that are on there, and a number of other pieces of equipment that actually contribute to Google's sense of location and direction and other things that enable that autonomous behavior. As far as mapping goes, we have a very similar set of equipment that goes onto the car. We have cameras, we have LiDAR sensors, we have radar, we have odometers, we have computers to collect all the data, and so to set the cars side by side, they actually don't look that different. So a car collecting a map and a car working in autonomous mode don't look all that different in terms of the equipment that they use. And coming from the sensor world, we always divided the use of a map into two broad segments. And really, the idea here is that in both cases, mapping and autonomous behaviors, we want to collect information about the environment around us, and we want to collect it in a very detailed way with a tremendous amount of information and detail in 3D mode. And we want to do it in a way that allows us to do one of two things: either store the data and then post-process it later and analyze it. And for example, a DOT might be interested in this data to say how many bridges are in my state, or how many fire hydrants in this particular city, or what is the status of my pavement and how badly cracked is it, and where do I need to deploy my crews in order to repair that pavement. So we want to collect the data and store it and keep it for future use. In general, when we talk about autonomous behaviors, and going back, several of us have history back to the DARPA Grand Challenges and other types of autonomous behaviors. Generally, what an autonomous vehicle needs in terms of its environment around it on the road is enough information to navigate on flat drivable road and to avoid obstacles that would cause either damage or other problems to the vehicle. So in that case, normally what would happen with a map is we would collect the data around us in a 3D mode, no different than the mapping would happen for the DOT, but we would analyze the data in real time, and once we figured out how to navigate based on the terrain map that we created, we would discard that data. So there was this kind of two ways of looking at this data collection. One is to store it, analyze it, and post-process it. Another is to collect it, study it, act on it, and throw it away. And what we're finding now is that these two worlds are converging. And the reason they're converging is because there seems to be more and more use for a map stored on a vehicle that is in either autonomous mode or has safety systems that can benefit from an onboard map. And I'll give you a couple of examples. Let's say we have a car that's using a feature called Adaptive Cruise Control, or ACC. And that adaptive cruise control is driving you along the road, and on board is a map that tells the ACC that in 100 yards there's a sharp turn to the right. If we have that information on board, the ACC can be smarter in anticipating that turn and slow you down before you get there. So you have a safer system on the car now. And that's just one of many, many safety benefits that actually Jim McBride will be talking about. Let's talk about autonomous vehicles. As it turns out, the number one challenge for an autonomous vehicle is self-localization. And what I mean by that is, if you're in an airplane and you're using GPS to localize yourself and you're off by a few meters, that's not a problem. If you're in a car and you're trying to use GPS to localize yourself, the best you're going to do is within about a meter or so on a consistent basis, and in many cases you'll have GPS dropout. That's not good enough. We have to self-localize the car to within a couple of inches if you're interested in driving in traffic and staying within your lane. The best way to do this is to pre-capture a map, compress it, have it stored on the vehicle, then as the vehicle drives, the sensors on the car collect information about the environment, and then on the fly we compare that to our stored map, and we say, oh, I recognize that bridge, and that bridge is at this particular geolocation, and now I know where I am on the road. And you can use that information to self-localize. So that's the number one issue. It's not the only issue related to that. So kind of as we see these worlds colliding, we have people from very different backgrounds who are going to be talking about how these worlds are coming together. We have Ray, as I said, talking about collecting data for the state of Utah for their DOT, and then we have both Jim McBride and John Leonard who are going to be talking about safety systems and autonomous vehicles, respectively. There is a question opportunity here. We're going to hold questions until the end of the webinar, but I think most of you should have a pop-up screen on the right where there is a question and asker field. Over there you can type questions in there, and then at the end we will be selecting questions and presenting them to our panelists. We'll also have a brief discussion time at the end there too. Ray, can you flip me forward here? I am a member of GTMA, and I wanted to touch on a subcommittee that's been formed that I actually am the chairman of. And it's interesting because this convergence of maps for DOT use and maps for autonomous safety systems and autonomous navigation use is getting a lot more attention as we look at this. So we're forming a subcommittee within GTMA, and Ray is going to talk a lot more about GTMA because he's really the father of our organization. But as far as the subcommittee goes, we are going to be discussing and making recommendations about the fact that DOT data is being collected. It's being collected and funded by either states or federally. And as they collect this data, and remember I said that the equipment used to collect the data is very, very similar to the equipment used to drive an autonomous vehicle. As they collect this data, our thinking is, why not advise those people doing the collection on maybe slight derivations they want to make in their collection procedures and slight derivations they want to make in their processing procedures to make this data available to those doing safety system and autonomous vehicle research. After all, these maps are in the public domain, and it could advance these systems forward and move safety systems and other types of systems forward so that we can help save lives, which is really why most of us got into this business. So we are trying to promote this discussion, and we would invite those of you interested in participating in this subcommittee to contact Rob Dingus, and I think we have that in the next slide here. We have his, I believe, phone information, or we have his email information here, rdingus@usgtma.com, or you can visit the GTMA website at www.usgtma.org. So with that introduction, I would like to turn the presentation over to Ray Mandli, and if I can give Ray a brief bio here. Ray is the president of Manley Communications. Based in Madison, Wisconsin, Manley is an industry leader in the design and development of highly specialized digital imaging, data collection equipment, and operational methodologies for various departments of transportation, DOTs, throughout the world. Since 1983, Manley has made available to the transportation industry a complete range of imaging, pavement, and positioning equipment. Together with a suite of supporting GIS software and services, Mandli has enabled their clients to design, manage, and maintain safe and efficient road and rail networks. Mandli has worked with over 30 states across the country and has brought technology solutions to several nations outside the U.S. Mandli currently functions exclusively from their Madison offices. The corporation has employees with various skill levels in engineering, business, sales, production, programming, human resources, data collection, data processing, and management. So here now I give you Ray Mandli.
Thank you, Bruce. I want to start out here first and just talk a little bit about the Geospatial Transportation Mapping Association, GTMA. A couple of years ago, I ran into Rob Dingus, our president, at a pavement conference, and we started talking about what the potentials were in the industry to try to create congruent data. So we decided to put together a charter as to what would be an association that could actually help the industry grow and become more diverse, or take that diversity and bring it together. So it's a cooperative effort of the industry professionals who provide geospatial transportation mapping devices, materials, and services. And our goals are to promote our industry, initiate the guidelines and best practices. This stuff is fairly difficult to do, so you need to set out opportunities for training, standards come out, try to get that information out to people so we do the best we can with our technologies, but also to develop those educational programs and maintain relationships with both government agencies and other trade associations. So we didn't want to lock ourselves out as just the industry. We wanted to be able to reach out to the government agencies, which fund a great deal of the work that we do, and also look at the other trade associations, looking at people like APTA and MAPS, and try to create bridges there so that we can all work together and solve problems. But we have a little special area that we're kind of looking at here, and that's in the transportation mapping side. That being said, I'm going to take you on a tour of our project in the state of Utah. This is going to start, data collection starts this coming week, and this is kind of a far-reaching project. We've done work like this in states like Tennessee in the past, but Utah brought it all together. It was a department-wide effort, traffic and safety, maintenance, structures, motor carriers, and asset management. They all got together and they tried to put together an opportunity to see if they could gather data that could be done in one pass, but be able to populate many of the different databases they need to work with. Big key here was to geolocate as many of the integrated assets as possible in the single pass and get the highest quality data possible. So we're looking at some very high resolution systems, and some of those systems complement each other to give us the potential high quality data that we need to be able to make decisions on the back end. So the original assets that were brought to the table when Utah first was looking at doing this were the pavement distress, signs, surface areas, GPS. Once they got to see what they could actually get from the data, that there was more things that could be extracted, additional assets were added, like ramps and collectors, barriers, walls, pavement markings, bicycle lanes, signals, sign retroreflectivity, structures, and overhead obstructions. So what do we use to go out and do this? Because you have to travel at highway speeds. Our goal is to be able to do this without causing any change in flows of traffic. An average system for us to do this kind of work, we'll start out, it's usually a vehicle that has a bunch of sensors placed on it. We'll start from the front end, the road surface profiler. This is our device that gets the running information and the IRI, the International Roughness Index. We have right-of-way cameras. We use various GPS systems. We have a lot of Planix POS LV systems. To supplement that, we have a wheel encoder. And then the high-resolution systems on the back, we have the LiDAR system. And we also have the LCMS. That's a laser crack measurement system. Inside the vehicle, you have to have a very strong power plant, and this is actually a server room on wheels. We have an equipment rack. Inside of it, we have our main CPU. We have the power and GPS control. peripheral processing unit to do any of the real-time work that needs to be done with the data streams, and our pavement control package. In the front end of the vehicle, we have an operator station. We use several different kinds of monitors and input devices. We usually run with 2 people in the vehicle. One is an operator and one is the driver. We try to keep the driver from having to deal with any of the operation of the vehicle. We do give status updates to the driver, but we keep that for safety's sake a separate part of the plan. Again, looking at the front area, you can see the main operator monitor, the right-of-way imaging cameras. We have a rear camera monitor to make sure that we don't back into anything, and we can also look and see what's behind us. The keypad there. So in the Utah project, and these are specifics, I'm going to show you pictures of the actual vehicle that's about to leave our offices. We're using an HCL 64E. It's one of the standards in the industry. There's a lot of different LiDAR products. This one gives us kind of a field of view, and it works real well for some of the object extraction we do. It has 64 lasers, 360-degree rotation, 1.3 million points collected per second. Has about 120-meter range, and it collects measurements and intensity. On the front of the vehicle, we're using a product from ARRB out of Australia. It's called the Hawkeye, and it gets our International Roughness Index, our macro texture, longitudinal profiles. That's a profile down the wheel path, and it's compliant with all international standards. This is a key piece of the technology that we've added. We've been using this system for about a year now, but this was very integral in us receiving the award for the Utah project. This system does both 2D and 3D pavement imaging. It collects running, distress, macro texture, cross slope, and longitudinal profiling. It's a lot of different pieces that we used to use a lot of different sensors to get. And the 3D pavement imaging is very important for us in our ability to do automatic pavement distress rating. In this particular configuration, we're going to be using a 3-camera system. Each camera is 8 megapixels. You can see the photograph there. That's actually from a project that we've done in the state of Hawaii. And this is the complete vehicle. This is the vehicle. If you go to Utah this summer and you see this running around, you'll know what it's for. The front view there, you can see the RSP on the front measuring the running data. Right up on the upper left side there, that is our sign reflectivity system. And then you can kind of see towards the back the LCMS, and then the LiDAR heads behind the back. The GPS antennas are up on the top. Here's a back view of that. So now I'm going to switch over to a workstation demo, because that's one thing to be able to go out and run these vehicles down the road, but you got to be able to have a way to reduce that data. And this is our environment. We call this our road view workstation. Now, the workstation, as you can see, has a lot of different data sets that we're demonstrating or showing at this time. You can see the imaging on top. We're zooming in. See the resolution of our cameras. This is a shell that's over an Oracle spatial database for this particular project. All the data is geolocated, and all the data sets are synchronous. So as we travel down the road, you can see all the different systems, or all the different displays will keep up with our data flow. Now, one of the main reasons we're in the Utah project is to do the road condition data, and this is using the laser crack measurement system, and we have the 2D image here that's created. And if you look at it, we get very high resolution images of the pavement. Cracks show up as black, but also many other things show up as black. So although this is a very nice way to be able to look at the pavement, you can't always determine automatically whether or not a black mark is a crack. So we go to the ranging image. This is the 3D image of the pavement. And from this, we can actually find between the peak lines there, you're seeing the wheel paths. We can determine different anomalies in the pavement. We have the cut crack that's there shown at the bottom. And then we have the pieces where you have cutouts for repairs. We can also find the distresses. Those are the smaller pieces in this particular image. I'm going to show you some big distresses a little bit farther down the line here. So the black in that picture gives us our depth. Okay, now we're going to look at some of the high IRI, roughness and distress. Jump over here. You can see the two pictures here. We have the 2D on the left and the 3D on the right. And if you look at the close-up of the 2D image, you're not really seeing some of the distress over there in the upper left, where on the right that distress is magnified. And all the little colored lines, the squiggly lines you see, those are the distresses that we're picking up with our algorithms that are used to find that distress. Now we're going to take a look at the assets. Another big safety feature is the guardrails. Guardrails come in many sizes, shapes, and forms. What we are capable of doing is finding those items and giving them, being able to define what type they are, where they are, and how they're set up. And there are standards for that, and it's our goal to be able to find out if what's out there is meeting those standards. Here's an example on a 2-lane road here. And here's our guardrail off to the side. As you can see, our pavement distress there, there's some distress over there in the lane. Now we're going to switch over to the curvature side. As you can see the photograph up above, those beautiful mountains in Utah. This is data that we actually took from the demo portion of our bid at Utah. We're able to get the grade data. You can see that in the table. Now we're going to look for a sign. I just want to remind everybody this is real time. This is working with our workstation environment that we developed and needed for us to be able to handle this data. This is how we reduce the data. And now to kind of bring this all together, I want to show you the point cloud from the LiDAR. This helps us to go in and be able to do all the measurement. As you can see in the upper picture, we do have, well, let's see here. We're coming up on a bridge. I'm going to show you some of the vertical measurement capabilities we have. This is, again, all these pieces put together. So we're able to automatically find the vertical measurements, and we can pick a bunch of different variables for that. But the red lines show us the lowest points underneath that structure. But we can look at all points underneath there. We can tell if there's an area that's of concern if you're going to be routing traffic. Now, if you take away the point cloud, now you're looking at all the data that we've collected, the area of the pavements, the different types of pavements. there's paint stripe data. So you can go in and you can click on all this data. It's all in easy to access. Do searches on it. Retaining wall. Okay, now we'll bring that LiDAR back up. Here's a sign bridge. We actually started doing this kind of work in the state of Texas in 2008 and have really refined our process. But we're finding the sign and we can create an actual, take out of it an actual structure that can be defined. But you can see all the different heights over each lane. If we take the point cloud out, you can see all the measurements that we've made. And this is the environment that Utah will have inside their offices to parse through the data and find the different assets they need to be concerned about for maintenance. Okay, with that being said, we're going to have you switch over to Jim McBride, Jim McBride, and take it from there.
Thank you, Ray. If I could introduce Jim. Dr. McBride has been a member of the research staff at Ford Motor Company since 1984, where he has applied his education to a wide range of physics-related disciplines. Although he is nominally a solid-state physicist with expertise in lasers, optics, and X-ray crystallography, he's also meddled around with topics such as alternative energy devices, exhaust gas catalysis, biophysics, nuclear physics, ultra-high pressure physics, and superconductivity. Recently, however, his research has focused on deriving automotive safety applications from the study of autonomous vehicles. Notably, he was the leader of one of only 6 teams to participate in the finals of both the desert and urban DARPA Grand Challenges. Over the course of his career, Dr. McBride has collaborated on projects with numerous national labs, governmental agencies, universities, and corporations, and has published over 50 peer-reviewed articles and presented more than 100 talks. I give you Jim McBride.
Thank you very much, Bruce. I like to tell people in my former life as a physicist, primarily what you do is smash things together and see what happens. And now that I've moved into active safety, what we try to do is not let things smash together. So it's a little bit of a paradigm shift for the way I think about things. But what I'd like to do today is to talk about how some of these maps impact future driver assistance and active safety features. And on this first slide, I'm showing at the bottom here a picture of our F-250 driving in the first of the DARPA Grand Challenges that we competed in. And while I do a lot of work in autonomous vehicle studies, I'd like to focus today on how these maps can be used for many, many other things, and in particular advancing safety features on existing products. So before I move on, I'd also like to point out that nearly everything you're going to see on the slides here today has been published in collaboration with our alliance partners at the University of Michigan, who I'd like to thank very much. And I can direct you to publications if anyone's interested in the future. I'm going to take a bit of a diversion on this slide here. I stuck it in at the last minute, and it kind of goes to the point that Bruce was talking about earlier. And if you just look at the top panel of 4 pictures here, the 3 on the left are fairly common scenarios where you might see vehicles coming at you, and it's not readily obvious if they're in-path obstacles and they pose any concern or not. And you can imagine the different sensing modalities as having problems with these. For example, on the left, a camera or a LiDAR system is clearly going to have problems with the reflection due to the water on the road. And in the middle, some things don't work so well in snow. And if your algorithms are predicated on the fact that you need to see the lane markings on the road or the intensity of the road, you might be in trouble. And on the next view here, the car you see in the distance, you can't really tell if it's in your lane or not because the road appears to be curving. And just for fun on the right, I can't quite see it myself here, but there was a proposal by some European company that the back of semis actually project the image of what's in front of them. So if you look carefully at that semi, you can see that it's obstructing the view of a red car that's coming around the bend out of view from it. In addition to this issue with sensors, and let me back up just a little bit to the example that Bruce gave. Suppose you do have an adaptive cruise control system. Most of those are predicated on a radar finding the range and azimuth to a target. And if you're going around a turn and there's a guardrail or the car appears to be in a different lane, it takes an awful lot of processing power to filter out the false positives from what's really true. On the other hand, if you had a map and you knew that the road was going to go in that direction, and if your map had annotated guardrails and things like that, you could vastly improve upon the robustness of where those false features are and make it work better. Similarly, I'm not going to dwell too much on these next two panels, which I plucked from another talk, but a lot of times when you're sensing things, you can run into things that are topological problems, and I wouldn't want to navigate that traffic circle on the left, nor would I want to try to figure out the scene on the right, which roads are on top of the others just from a camera sensor. If it's in the map structure and if it's 3D, it makes the problem much simpler. And on the bottom here, I've actually driven both of these roads, and a lot of people would naively expect that the more dangerous of the two is the Bolivian Death Road. And in fact, a lot of people do go off the edge there, but from a sensing point of view, that's actually quite easy to see because there are huge discontinuities in the elevation profile from the left to the right, and it's pretty easy to see where the center of the road is. On the other hand, that segment of I-15 in California actually is one of the more dangerous roads in the United States. It's very flat in places. It's very long and drawn out, and the median strip between the roads has a huge discontinuity in the materials. It goes from concrete to gravel, and if you put wheels on gravel, you have a differential, what we call a split mu condition. You have a differential friction on the two sides, and it very often results in bad behavior such as rollover. And again, if that were annotated in a map, based on knowing the difference between concrete and vegetation or something, that could be very useful. So here's a picture of our truck as it presently exists. And we mainly use this truck not for autonomous driving these days, but more as a research-grade platform for acquiring maps and making algorithms that push forward our safety features. And this is a close-up of the sensors on the roof. On the left, you can see we have two Regal LMS Q120 airborne LiDARs. These are typically used for reconstruction of Earth terrain from flying above. They're very high precision, 0.02 degrees per step size, but they're only one single beam. They're not a live picture. In contrast, you have the Velodyne sensor, which at 10 hertz gives you a 360-degree live view. And we also have a corresponding omnidirectional camera from Point Grey Research. And here's a scene from right outside my front door of what one frame of the LiDAR and one frame of the camera would see. So it's basically a 360-degree picture. In the top view of the range to everything, colored by height above the ground plane, and in the bottom, the optical image, and that's about a 12-megapixel picture there. So what we'd like to do ultimately is to combine those two images. And so in the top frame here, you can see that we've overlaid the LiDAR on the camera image from outside our research building here, and we've, for the point of clarity, subtracted anything that's in the ground plane. So all the remaining points are things that stick out of the ground and could potentially pose hazards to where you drive. One of the great benefits of fusing the data is, if you look in the left panel here, I think I've drawn a yellow arrow there. You can see that there's a sign saying a pedestrian walkway or something to that effect sticking out of the ground in the road. You do not see any LiDAR points on the shadow, whereas in a lot of vision algorithms, that shadow might actually look like it's an obstacle. And it's very clear to pick out that it's not an obstacle because it doesn't appear in both data sets. And I'm going to try to play for you an image of something in motion from the bottom scene. This happens to be driving in downtown Dearborn in November. And as you'll see later, Dearborn in November is very, very gray. I'll probably play the video twice because from Windows and from another viewer it renders differently, and some of you will see it better one way than the other. So what's happening here is we're just driving on a divided section of highway through downtown Dearborn. It's US 12, and you can see that, again, we've subtracted everything in the ground plane, and anything that's coincidentally registered in the camera and the LiDAR data appears to us as an obstacle we should be concerned about. And you'll note that our data seems to be truncated fairly low to the horizon because we don't typically think that cars are going to be flying above the surface of the ground. So we leave the Velodyne in its natural reference frame, which is about 2.5 degrees above horizon. And I'm going to quick jump out of here and play this in another viewer in case it didn't render for some of those of you who are watching. I believe this viewer goes at half speed. So again, what you're seeing is everything that's co-registered between camera and LiDAR gets colored unless it's in the ground plane. And I think that should probably give you an idea of it, and I can move back to the PowerPoint slides here. So ideally what one would like to do is to fuse the LiDAR and camera imagery. And I'm going to show you an example in these two panels of doing just that. And the previous examples were either run live or showing one frame of data. And in our case, one frame of data is a 1/10 of a second. In these two panels, I've aggregated 10 frames of data, so 1 second's worth of motion of the vehicle. And in the top frame, you can see as the truck moves along, we're starting to fill in the entire surface with the laser beams hitting everywhere. And in the bottom panel, what we've done is we've taken the intensity channel from the LiDAR, and we've, on top of that, put the color from the camera. Now, for most of you, you're going to probably look at that and say, well, that looks black and white. I don't really see any color. And it's because November in Dearborn is largely devoid of color. There's gray asphalt, gray skies. Pretty much the only thing that isn't gray here is if you look carefully, there's a couple of yellow painted lane markings and an awning or two on the building. You'll see some more data of this coming up. I'd like to point out that this drive that we took starting from this initial location and going through downtown Dearborn has been published as a data set online and is available for the public to download and to test their algorithms against algorithms that we've published in the literature, and basically to work with it and see what they can extract from it. And the key point here is that in our case, every pixel in the LiDAR and every pixel in the camera is very precisely co-registered and aligned in time. And this paper listed here is one of many that I can send to people who are interested. I'm going to briefly step aside here and kind of generically talk about the idea of something we call simultaneous localization and mapping, or SLAM. John Leonard's going to talk about this in more detail in a minute, so I won't dwell on it too much. But the premise is, if you're out in the world as a robot or a mapping vehicle, you can both make a map and figure out where you are within that map at the same time. And taking any sensor mode, and I've shown 2 frames of LiDAR data looking from above at 2 different instances in time. And if you'll notice, I've extracted a handful of features in each of these images. And for example, look in the bottom right corner at features D and E. As the vehicle's moved from frame 1 to frame 2, not only has it moved a long way past D and E, they've actually switched order. There's a retrograde motion to where they seem to be located. And by tracking these features and the millions and millions of other features that you get from the huge array of data that's coming at you, you can very accurately tell how far the vehicle's translated at the same time you're creating a map. And again, John will talk about this in more detail. The point I wanted to make is from the Utah data that's being collected, there will be a LiDAR point cloud, and one of the ways of doing localization is based just on using the LiDAR alone, and I'll show you an example here. On the left, we have our vehicle in the middle of a lane near our Dearborn proving grounds. It looks sort of like the horseshoe clam. That's the shadow mask underneath the vehicle. Just to the right of it is another car that's creating a big shadow as well. In the right frame, I've taken a picture of that vehicle at a time when it's traveled further down the road, and I've added a bunch of noise to it. I've added some lateral offset. And the question is, taking these 2 sets of data, can I figure out where I am using an algorithm that it is known as ICP, or iterative closest point, or sometimes also referred to as closest point to plane. So on the left, I've just superimposed the 2 previous images that you saw to show you that they really aren't aligned. And then after we run the algorithm, what results is the picture on the right. And you see that between the green image and the red image, everything is aligned except for the shadow underneath the vehicle, which is moved forward along that lane by about 5 meters. This algorithm works fairly well when you have an initial guess that's good, and when the frames of data are rich enough in detail and not too far apart. And sometimes if you get the frames of data too far apart, or there are not enough features, that algorithm can fail to converge. And so in this case, the power of having a camera on board is really useful. So what we do is we seed that algorithm with camera data. And so on the left is a picture like you've seen before, where we are overlaying LiDAR points on top of the camera data, removing things that just hit the ground plane. On the right, we're picking out something called scale invariant feature transform features, and to you and I, they don't really look much like a feature, but the point of this algorithm is to find things in the camera data that sort of look the same from a whole variety of perspectives and scales, different distances, and what angle you're looking at them. So something that looks very bland might be great for this algorithm, doesn't seem so great to a human. So taking those points that have been pulled out of this image and preceding that prior algorithm results in this map here, or I'm sorry, this graph here. So on the top blue line, what I'm plotting here is how big of an error one could end up having in guessing where the vehicle is localized based upon how far apart two subsequent pictures or scans of data were. So, you know, up to about 5 meters, if you have two LiDAR point clouds, the convergence is pretty good. But once you get beyond 5 meters, the chances of getting a great locked-in convergence rapidly go down, and the error goes up to many meters. You wouldn't stay in the lane. But if you feed the data with the camera data features, you can see from the red line in the graph here that we maintain convergence even if the two subsequent frames are maybe as much as 20 meters apart. And this gets to a point that I'm going to want to repeat several times, is that fusing the data at the raw level is the most powerful thing you can do. And if you're going to fuse the data at the raw level, it's absolutely imperative that you know the calibration between all your sensors, that you know the rigid body transformations, that you know the calibrations, that things are accurately time-stamped and they're co-registered at the pixel accuracy level. I'm going to show you, this is a standard loop we do around downtown Dearborn, and as you can see, even in the summer it's fairly gray in appearance. And what I'm going to show you is that the data is fairly robust even against time. So I'm going to take a map that we took in 2009 and use that to try to figure out where we are 2 years later in 2011. And up in the upper left-hand corner here is the parking lot where you saw the image before that didn't have very much color. And that's our starting point in the loop. And so here's what the images look like in the summer or fall of 2009 and the winter of 2011. You can see quite a bit has changed. Similarly, from other points around that loop, which is, it's roughly about a mile loop in downtown Dearborn, you can see that there's quite a variation in scenery. Like on the bottom right-hand corner, we go from having you know, trees with no foliage to leaves to snow on the ground. And I don't want to dwell on this. I think John will probably touch on this as well. But in this case, we're going to use a camera-only algorithm. So as I showed in the previous slides, you can extract features from camera images. And so if I back up one slide, one of these pairs of images here was a set of condominiums that we drove by. So we've just picked one of these, and from the vertical structure of this building, we've picked out some of these SIFT features. And again, they might not look like much to you, but we pick those out around the route. And in the right portion of the slide here, you can see the rectangular route we've driven, and we've placed all those features in here to show you roughly how dense they are on the ground. And these features are in addition to features that might actually be in the ground plane, but it turns out, you know, having features out of the ground plane is very useful. And this is a 128-dimensional feature space, and we have methods to compress this space into a smaller size, and it's basically it's fairly technical. I don't want to go into the details, but we would do hierarchical clustering in something known as a vocabulary tree, and I think it's better explained by this next slide here anyway. In the top line of the table here, the raw data for driving that roughly mile-long loop, and by raw data I mean all the LiDAR and all of the camera data coming in at camera frame rate, was about 110 gigabytes. Now, after we extracted the camera features and we put them into this vocabulary tree to to shrink them and did some subsampling, we can get that down 4 orders of magnitude in size to about 12 megabytes. So what does 12 megabytes mean? Well, there are about 4 million miles of roads in the United States, and we generate from the data we're taking about 14 megabytes per kilometer, and that translates to about, if you wanted to serve that data over a cellular network, for example, that translates to about 30 kilobits per second per kilometer per hour. So in other words, on a 3G network, we could deliver live anywhere between 0.2 and 2 megabits per second of data. And on a 4G network, we could deliver, upwards of 10 megabits per second of data, which is absolutely plenty to serve up the camera features from that algorithm. The interesting thing about this algorithm is if the ground were, for example, covered with snow and you were relying on seeing the reflectivity of the surface in the LiDAR, you don't really care because you have feature points that are on vertical structures such as that building. And just to show you the power of this, one of our graduate students has prototyped this algorithm on a smartphone. So he can drive around and collect with a smartphone these same camera features. Now the smartphone isn't adequate to give an XYZ coordinates for all of the features. It can identify them, but given that we have this really high resolution survey map, once we've identified the features, we can look up where they are in space from our survey grade map, and then using that we can keep ourselves localized within a couple of centimeters in the lane of travel. And that's what's really important, is knowing where the vehicle is relative to all the other things in the map, the lanes, the buildings, the intersections, the signs, and the moving traffic and things like that. And with that, I think I'm going to hand it off and let John talk about some of the more theoretical aspects of SLAM.
Thank you, Jim. Oh, John, this is Bruce. Can I introduce you?
Yes, please.
Okay. John Leonard is Professor of Mechanical and Ocean Engineering in the MIT Department of Mechanical Engineering and a member of the MIT Computer Science and Artificial Intelligence Laboratory, or CSAIL. His research addresses the problems of navigation and mapping for autonomous mobile robots. He holds the degrees of BSEE in Electrical Engineering and Science from the University of Pennsylvania and a Doctor of Philosophy and Engineering Science from the University of Oxford. He is a recipient of an NSF Career Award, an ETS Walton Visitor Award from the Science Foundation of Ireland, and the Kung Sun Fu Memorial Best Transactions on Robotics Paper Award in 2006. Currently, he serves as Area Head for Ocean Science and Engineering in the MIT Department of Mechanical Engineering and as Co-Director of the Ford MIT Alliance. John?
Okay, thanks for that introduction and this opportunity to speak. I wish I had more time to do justice to these topics. I could speak for 2 or 3 hours, but I'm going to give it a shot here and really try to talk about 3 different topics. Just a brief introduction to autonomous vehicles, some pointers to things that are out there on the net and that people can look at if they want to find out more. A description of the problems of mapping and localization in robotics and some of the ways we approach them. And then I want to close talking about publicly available data sets and the power of open source software development and the potential that if data is made publicly available, that there is an army of researchers out there in the world that would devour such data and use it for good purposes to advance algorithms and develop better systems. So in just a quick introduction to autonomous vehicles, if anyone's not familiar, I know we have a very broad audience on the call. I just picked a couple notable things in history. So Professor Dickmans from Germany developed pretty amazing capabilities back in the 80s and continued through the 90s. And I just recently found a YouTube video that's referenced here of his keynote talk from last August at an artificial intelligence conference in California. So try to watch that if you can. But the amazing thing is they achieved vision-based navigation back in 1987 on a German roadway. And another really important historical figure is Professor Chuck Thorpe from Carnegie Mellon and his colleagues, such as Takeo Kanada and Dean Pomerleau. They developed a sequence of vehicles called the NavLab vehicle that went through many iterations but achieved quite sophisticated autonomous driving. This is one of the notable early U.S. efforts. There's also some early efforts in Japan that I'm a little less familiar with. And one thing that the Carnegie Mellon Group did, well, first of all, there's a wonderful archive of historic academic papers. So I am an academic roboticist. I want to advance the field of research, and that's why publication is so important. And there's a lot out there. You can look in Google Scholar on some of these authors and see their seminal works and some of the issues. But one thing I pulled out for Carnegie Mellon is their No Hands Across America event, which they did in 1995, and they made it 98% autonomous, or at least hands-free, for across the country back in 1995. It's quite an amazing achievement. And so after those early efforts, I think you could safely say that autonomous driving, research, there were these strong groups that were making great progress, but the field really accelerated with the DARPA Grand Challenges. And so for myself personally, I'm going to click on a few videos here. I'm not sure how well they'll play on the webinar, but I was the team leader for the MIT entry in the third DARPA Grand Challenge, the Urban Challenge, and had an amazing team of people, faculty colleagues, Seth Teller, John Howe, David Barrett at Olin College, and we set out to develop a vehicle that could drive itself in traffic. And for us, like someone who drives in Boston every day, if you think about how challenging it is for people to drive, we were just captivated by how hard it is for getting a robot to drive in traffic, especially with sort of limited, uncertain information, prior information about the world. And so I wish I had an hour to tell the story of our team. I put in a little pointer here. There's a wonderful television show called Robocars on the Science Channel. It broadcast 4 years ago that gives a sort of inside look at some of the teams. And as a researcher going to the Robotics Challenge and seeing all the different vehicles, it was kind of like a Woodstock of robotics. It was just a wonderful event. And it gives us sort of insight into the more human element, I think, of developing these systems and how much fun, but also how much hard work and the challenges that's involved. And so but we were fortunate to be one of the teams that finished the challenge. And I'll say a little bit about our systems design and what we learned from that project and relate it to some other things that are happening today. So I think I'll stop here and move on to say a little bit about the challenge. So the goal was 60 miles in 6 hours, with an emphasis on safety and trying to exhibit sort of advanced behaviors in traffic. For us, we really aimed to develop a system that could use very limited a priori information in terms of the exact waypoints to follow and the exact structure of the road network. So one of the earlier speakers talked about this sort of server on wheels. We certainly had that. We had a blade cluster with 40 processing cores, and we needed a 6 kilowatt generator to power it, 2 kilowatt air conditioner on the roof to cool it. And why did we need so much processing? Well, we had a lot of sensors, and we wanted to do a lot of advanced algorithms. We tried to use vision to perceive the road in real time and make decisions in real time based on that information. And so very briefly, no time to really do it justice, but how does a vehicle like this work? Well, this is a rough overview of our system architecture, and sort of on the left-hand side, we have the planning and control and decision-making, where sort of a high-level navigator gives the vehicle waypoints and feeds into a motion planner that gives it a trajectory, and then a controller that tries to follow that trajectory. And then on the right side, sensors. So we have vision, LiDAR, inertial GPS sensors feeding into perception modules that would try to detect obstacles, detect hazards, things like curbs and concrete barriers, and to detect the lanes. And this information fed into something we call the grid map, or the local map, that is sort of a sliding window that moved along with the vehicle, giving a picture of what is where in the local environment, what is safe, what is not safe. And this all had to run in real time, and it took extensive testing and system integration to get to the level we achieved in the challenge. And one of the really important sensors was a Velodyne scanner. And so really making the decision to get that sensor was really important for our team, because giving that massive amount of data, 1 million data points per second, it really is an advance over other technologies. But even with all that data, it is still quite challenging. This is a video, if you can see it, of driving our vehicle down Mass Ave towards Harvard Square, and sort of making sense of that data to detect people, to detect cars, detect trees, and other static obstacles. It still is quite a challenge to do that in real time. At least it was in 2000 and 2007 and 2008. Now, if we so looking back on the DARPA Urban Challenge, you know, Carnegie Mellon, Stanford, Virginia Tech finished first, second, and third. They did an amazing job. For MIT, it was our first entry. We were just hoping to finish, and we came in fourth. We were one of the 6 finishers, along with UPenn and Cornell, who did an amazing job as well. If I'm looking back, and so I was really asked to speak about the importance of the base map in this whole area of the autonomous driving. And just briefly, if you think back to the early Dickmans and the Carnegie Mellon NavLab work, it was trying to use vision in real time to sort of follow lanes, but less emphasis on an exact prior model, certainly not a 3D sort of point cloud model that the technology is becoming available today. And if you look at Carnegie Mellon, led by Chris Urmson, who as sort of the lead, technical lead, they had their system is very well described in their journal paper from 2008 from the Journal Field Robotics Special Issue, and they what their paper says is, you know, based on waypoint density and aerial imagery of the Urban Challenge final event course, the team determined that there was not a need to estimate road shape online. And so just a little background here is we went into the challenge assuming that DARPA wanted us to sort of make the map to some extent and localize in real time. And this is what we call SLAM, as Jim mentioned. I'll say a bit more in a minute. But what Carnegie Mellon and Stanford both realized is the sort of one of those obvious in retrospect things is if you could predetermine the path of the vehicle very precisely, so give it a really precise trajectory to follow, then you can greatly simplify the whole enterprise. And so for this challenge, you could use GPS to do that. DARPA, in the end, did give us prior maps, which you could use to go in and make very precise routes to follow. Our team didn't do that. We tried to do it more based on online vision. And we had a PhD student, Albert Wang, who's just a wonderful coder who implemented under Seth Teller's supervision to create a real-time system for detecting and tracking lanes that we integrated in the whole system. And so for our system, because maybe there's sunlight, shadows, there are times when vision will get confused. And if you rely too much on vision in such a situation, your vehicle's going to get stuck. It's going to sort of stop and think, like right now, the video sort of stop and say, I'm not sure here, I should stop. So our vehicle is a little safe, and that's why it was a little confused at times, but that's a long story, but we did finish the event. And so at the end of the day, what did we learn? We learned a lot in terms of research. Now, I'm going to fast forward just a few years forward to October 2010, and not a lot of time, you know, really in historical sense, but the amount of development in that time is just stunning with what Google came along with. And so I remember seeing the Sunday New York Times on October 9th, 2010, and there was this front-page article, Google cars drive themselves in traffic, and it was really a sort of a landmark day in robotics when this project was announced. And there you can see in the picture on the roof the Velodyne laser scanner, you know, which clearly gives us enabling capability for using the getting 3D dense point cloud information and mapping it against prior maps. And on the day that project was announced, there was actually a second article in the technology section of the New York Times, which was more of an interview with Chris Urmson about the technology being used. And for me personally, this was also sort of a landmark day because if you go forward, there's a paragraph from that article. One main technique used by the Google team is known as SLAM, or Simultaneous Localization and Mapping, which builds and updates the map of the vehicle surroundings while keeping the vehicle located within the map. And it talks about how they make the map in advance, annotating it and so forth with human help. And then when they're autonomously driving, they do have to still detect changes if the map's not up to date. But in general, the map just gives you this ability to make the perception and localization problems a lot easier. So you can use the map to localize, to figure out where you are, and you can also use it to ease the perception problem by sort of almost filtering out the things that you expect to see. You can focus on the unexpected. So for me personally, this SLAM problem is actually what I've worked my whole academic career on. And so it was, you know, I think I recall calling my mom and saying, hey, SLAM is in the New York Times today. You know, it's good to see things sort of evolving over the years. So now I'm going to say a little bit more about SLAM technology and why I think it's relevant to the enterprise of mapping the nation's or the world's roadways. And so just a quick introduction to SLAM if you've never seen it. The goal is to make a map from sensor measurements which have noise in them. But you also have to estimate your vehicle trajectory, because if you don't know where your vehicle was, then that uncertainty will mess up your map. And it's been said, I remember writing a paper 20 years ago for a conference in Japan saying, simultaneous map building and localization, which came first, the chicken or the egg? The idea is that you sort of need to know where you are. You need the localization piece to build the map. But you need the map to localize yourself, and you're trying to do these things together. And that's where the simultaneous part comes in. But so in general, when you're performing SLAM, we have, here's a little video I'm going to play. This is a famous historical data set from University of Sydney in Australia, just driving a pickup truck with a 2D thick laser scanner around a park, Victoria Park in Sydney. And the trees in the park serve as landmarks, shown here in green. And the measurements, ranges to the trees and bearings are shown in yellow. And you see two trajectories. One is the vehicle's dead reckoning or odometry trajectory in blue, and then red is the SLAM corrected trajectory in red. And the general problem with dead reckoning or odometry is that it's going to drift. The error is going to increase with time. And with SLAM algorithms, what we do is we correct for the drift in the dead reckoning while concurrently making our map. And so if you, and just as a pointer for those that are interested in terms of the academic work in SLAM and how it underpins some of this, there's a large academic community that pursues SLAM. And one good place to look is there have been 4 summer schools, sort of a week sort of school just devoted to SLAM. I was fortunate to be at the first 2. This is a picture from the first SLAM summer school in Stockholm, Sweden. And in general, we've made a lot of progress using what we call postgraph optimization techniques. And there's some great literature out there I can point anyone to if they're interested in. For me, there still are research issues with mapping. And a big challenge is, how do you handle changes in the world? So if you map the world and the world the world changes, and you now have a mismatch between the map and the world, that's an issue. So how do you sort of maintain the map? How do you achieve persistence and robustness as you operate for longer and longer times? So so that's a bit on the mapping problem. And just in terms of how we attack it with probabilistic graphical model algorithms. And there's a whole literature out there. I can think of many good introductions. There's a Udacity online course on autonomous driving that is freely available to the world. There's some great sources of information out there in the academic community. So at that point, I want to shift to my final topic, which is the issue of open source software tools and the power or benefits of publicly available data sets. So in our own group, in the DARPA Challenge project, we had some amazing students, Ed Olson, David Moore, Albert Wang, that created something called LCM, Lightweight Communications and Marshalling. This software handled all of the messaging and data logging and replaying and visualization of all these massive data sets. Another thing that's out there which has just tremendous momentum in the community is ROS, the robot operating system, which is supported by Willow Garage and now the open source software, the Robotics Open Software Foundation. And part of ROS, or related to ROS, is something called PCL, the Point Cloud Library, which is some routines that let you deal with large amounts of 3D data, visualization, and processing, removing uncertainty. And more into, so there's sort of the tools for handling the data, and then some of the algorithms for doing the estimation. My group works a lot with SLAM, as do colleagues around the world, places such as Freiburg and Oxford and Georgia Tech. And so there are many good algorithms out there. And but another thing in addition to the open source software is the data sets. And so from the DARPA Urban Challenge, our team made its entire data set, so over 200 gigabytes of data available freely on the internet. And that's been downloaded many, many times by people around the world. In robotics now, we have what are called data papers. So the Ford campus data set from University of Michigan and Jim McBride at Ford, they have a paper that gives the sensor data, and not just the data, but the calibration and the description of the sensors. And those things actually really help the community make progress, because one researcher develops an algorithm and compares it against another researcher's algorithm on the same data, and we can actually see progress. And so the bar for publishing is getting higher and higher and higher in SLAM, because there's so many things out there you have to compare against. And it makes it harder as a researcher, but it's actually a good thing, because it means we're making a lot of progress. And I just wanted to give you an example, there's time, of well, so here's a pointer. This next slide is just a pointer to our DARPA Challenge public page where we have some movies from our challenge and also pointers to the software such as LCM and the actual data logs. And I wanted to close with an example and this sort of personal sort of story of how I think the open source tools enable very rapid development. So I have some collaborators in Ireland. John McDonald is a researcher there and in computer science, and his student Tom Whelan. And they've taken many of you I would presume are familiar with the Kinect. The Kinect is I'll go forward and show that. So the Kinect is a sensor for the Xbox. It only costs $150. It's been out for almost a couple years now. And using the Kinect, you have a very low-cost sensor that can get direct measurement of depth. Now, it doesn't work in bright sunlight. It's really made for indoor environments. You may say, what does that have to do with mapping roadways? But in general, it shows the ability of putting the range information with the vision information and what you can do with it. And it also shows how rapidly things are happening today in the open source community. So Kinect Fusion was published in 2011 by Microsoft and Andrew Davison's group at the Imperial College in London. And there's some great, if you just look for Kinect Fusion on YouTube, you can see some really cool videos of sort of desktop scale reconstructions. And what Tom and John have done is to extend that and combine it with the sort of the SLAM algorithms to make it spatially extended and larger scale. And really in just a few months, building on all of the work of others made available through open source and through the community, then very rapid development is possible. And so here's just an example on the left is a reconstruction of Tom's apartment in Ireland, and on the right is a roadway scene with just a Kinect taken at night because the daylight would obscure the sensor. So if so I'm just going to play a video here that I probably don't have enough time to fully show, but just to give an idea of some of what's going on here. And so I think there's an opportunity here with the publicly funded mapping of the nation's road infrastructure for the tools from robotics to be used to benefit, and also for the data collected to feed back and benefit the research community. One of the challenges we typically have is actually getting data, and if we and so if you and in a so I think there's some great opportunities here. So what I'll do is I'll just close with just one more, putting the Kinect work, which may seem nothing to do with roadways, into the context of the actual project that the folks at Maynooth that I'm very much involved with, is a project called Strategy, funded by the Irish government, to map the road infrastructure in Ireland. My wife happens to be Irish, and when we go over there and drive on the country roads, she always tells me the undertaker loves the overtaker, which if you've ever driven on an Irish country road might make some sense to you. That especially where the road infrastructure is not improved, the sort of the windy roads going through old areas, and the potential for this 3D mapping technology to allow us to better capture the existing road network conditions, and then perhaps do simulations or make almost like models to make investments on how to make the road safer and reduce fatalities. And so this notion of sort of capturing, mapping the roads to as a basis for improving safety is something that I very sincerely believe in. So in conclusion, I just wanted to say that mapping and localization, these sort of couple problems, are fundamental research issues in robotics, and there is a large community out there making progress on these sort of challenges and moving to larger data sets. And there are open source software tools out there that might extend to the highway driving scenario. And please make your data public so that we can process them in the robotics research community. And with my final slide, I just wanted to close on the important issue of ethics and safety. When we teach, I teach an undergraduate design class here where we have a lecture on ethics, and we have to really, instill in our students the engineer's role, and sort of the, if you go to the National Society of Professional Engineers website, engineers shall hold paramount the safety, health, and welfare of the public. And so the idea of using these data sets to increase the safety of the public is very exciting. But also we have to keep in mind that safety of the public is the #1 issue. If any conversation about autonomous driving, I think we have to keep safety as absolutely first item and perhaps only item in the discussion. So at that point, we go back to the other speakers.
Thank you very much, John. We do have about 15 minutes more in our webinar, and there's still time to ask questions. If anyone would like to pose a question, you can simply type it in the question area on the right-hand pop-up menu. I'm going to pose some questions for our speakers. First of all, just as a general comment from my perspective, I thought it was very interesting listening to the different terms and vernaculars that the different speakers used. Ray using terms like collect, store, analyze, and both Jim and John using words like motion, SLAM, localization, things related to cars as they move forward. So you can see the different worlds starting to come together here and how we're trying to blend these two disciplines. The first question, or may I say set of questions, is directed to Ray. And Ray, if we can envision the fact that you're going to have a vehicle or vehicles roaming the roads of Utah, you're going to collect data on every single road within Utah. How long is this going to take you? How many miles per day in general can you collect?
Well, we're projecting right now that the project will take until about the middle of August to the end of August, depending on weather. Post-processing will take well into the end of the year. So the data itself in its final form will probably be available right after the end of 2012. The pavement data is the first area that we're going to be finishing, because there are requirements with Utah being able to report their data to the Federal Highway Administration for their requirements to get money in. And so that's going to get an emphasis in the beginning, and that's got to be ready by September. But the other stuff will be processing and bringing it down. It does not take us a long time. We've come up with ways to reduce the amount of time with computing power and automating a lot of the processes.
Are you using a single vehicle or multiple vehicles to cover the roads?
We have a single vehicle assigned to that project right now, but there is a backup vehicle. There's a vehicle that's will be ready in about 2 or 3 weeks that can be taken off other jobs, and we can configure it to do exactly what the vehicle that's taking off, the H2. We're using a Hummer H2 as the vehicle this year for Utah. But there's another van that has all the same sensors on it that will be doing other smaller jobs and can be brought on to supplement at the second half of this project. We have a projection date of about the middle of July, and a decision will be made whether that vehicle be brought in to do that work.
Okay. Are you, a couple more for Ray, because there was a lot of curiosity on your project there. Are you collecting sign reflectivity on this project, and are you collecting pavement markings, pavement markers, that type of thing on for this project?
Yes, we're doing a small sample of the sign retroreflectivity, a proof of concept. It'll be 1,000 signs. If we meet all the requirements on that, the next cycle will have 100% retroreflectivity collection. The pavement markings are all being captured. We actually will find all the pavement markings and be able to give area that the paint is actually on. So we do that using our LiDAR product, and we have a bunch of algorithms that will extract that data for us.
Okay. Question came for Jim. What are the safety systems that you see evolving and improving over the next few years? And I know you're doing a lot of that type of research at Ford, and to the extent that you can discuss this question, people are curious about what kind of safety advances should we be expecting over the next few years?
Well, I think it doesn't just apply to Ford, it's industry-wide. What you've seen in the last couple of years come online are adaptive cruise control systems, and for those of you who haven't driven them, once you do, you'll never want to go back. It's basically cruise control that maintains a gap between you and the object in front of you, and can do that by radar or camera. And what people don't often realize is that these systems come with some added things that run in the background. Because the radar is monitoring the distance to the car in front of you, you often in these systems get things like collision mitigation by braking. If you don't even have the system turned on, you still know how far things in front of you are, and you get assisted braking up to a certain threshold. And what you're going to see is that's going to continue to become more and more robust and operate over a greater envelope, effectively in the future bringing the car to a complete stop. And some car companies have already launched prototypes and are going into production with something they call traffic jam assist, which is basically the it's basically the cruise control all the way to 0 speed, so it stops and goes. So if you get caught in a traffic jam, the car's going to come to a stop. And you not only do that, you couple that with lane centering, and the vehicle keeps you centered in the lane behind the car ahead of you, and you just inchworm your way through traffic jams. So a steady progression in this sort of thing. Now, when you have the ability to add in maps, you can do a lot more complicated things. You can, as someone mentioned, you can slow the vehicle down when there's, hazardous road curvature. You can get rid of false positives from guardrails and things that, the radar might not think is in path or out of path. And all that on the production side is going to continue forward. And in parallel with that, you have researchers like myself who are looking at algorithms for essentially, being able to make a vehicle capable of driving itself. We might not necessarily use all of those, but if this car is smart enough to do it, those results can be spun off into other safety products as well.
That sounds great. Quick question for John, and obviously the achievement of MIT at the Urban Challenge was well documented and very, very impressive based on what your team accomplished. But weren't you involved in a historic event at the Urban Challenge? And if I need to spur your memory, I will.
Sure. Yeah, we were in a few little mishaps. So you might call them the first robot-on-robot traffic accidents. So that's what you're asking about, right?
Yeah. We didn't practice this, folks, but
yeah. So we had a little collision with the robot Carollo. It was in a sort of a parking area, or sort of like an open field area, and then we had a quite notable little collision with Cornell. I can pull up the videos of it if you want to see it. I think that because of some of the choices we made in our system about being sort of perception-driven versus trying to rely too much on GPS and the prior map, our system sort of, it had some, it just encountered difficulties in situations that were slowly moving obstacles and ambiguity as to where exactly it was on the road. And so we had a couple of mishaps, and DARPA said they sort of weren't our fault and let us continue.
Well, you weren't the only vehicle with such travails. There was a very large truck from a 12-ton truck that took out a parking structure. So we know of lots of examples of these types of things from the Urban Challenge. So thanks for that. Ray, if we can get back to you and more on your collection, there's a question on guardrails. Can you determine guardrail height and to what precision, and what kind of condition data do you collect on guardrails? For example, this one's been smashed in, or this one is intact. Do you do any work with guardrails?
Yeah, yes, we can do guardrails. We can get the height of them. We can tell if a guardrail is damaged through analysis. It'll show up that it doesn't meet the specification of an as-built. So we can identify that and then go back to the imagery and actually quantify it. Our accuracies are, with the LiDAR and everything, we're right in that 1-inch accuracy. So we can get it down. There's different ways to actually get it less than that, but it takes a lot more work, and you'd have to go slower. We can also pick up the types and ends of them, because guardrails have different types and ends, and that especially as in the last decade, there's been a lot of improvements to guardrails. So being able to tell whether or not something's been replaced, it has the right end on it to meet the federal requirements, that can be derived out of the information also.
Interesting. Can you read structure numbers that are stenciled on light poles? Because a lot of those are, they're geolocated, I know, but they also have numbers on them, right, that index them. Are you able to get that detailed?
Well, as you can see, we use pretty high-resolution cameras, but yesterday I actually signed a deal with EarthMine that we'll be working as a partner of theirs. Their multiple camera system is, I think, a total of 50 megapixels. It's quite an elaborate system. It gives us photogrammetry along with the ante in terms of the kind of sensors, and we are looking at some ways to try to get that, squeeze that into the Utah project, but other states are going to be having that be a standard that they're going to be putting into their bids. But you know, there are things that we cannot get. If something is less than a couple inches tall, you know, lettering and stuff like that, or it's at a weird angle, or we just have some weird lighting, there are things we just are not going to get. We've been asked to be able to read stencils on the backs of signs when we're doing the reflectivity work, and some of it, it's just not the right place for us to get that line of sight to it.
Mm-hmm. I understand. I was hoping to ask a question about my subcommittee, and I'm going to ask this to both Jim and John. And relative to the collection of the Utah data, and we're going to obviously discuss this a lot more at length in August at our first subcommittee meeting. What kind of, can you give me an example of the kind of advice you would give Ray for what data he ought to be collecting and or how he's post-processing it so that it would be the most useful to people doing safety system and autonomous vehicle research, either Jim or John?
Well, let me jump in because I kind of left this off in the talk. We collect from our camera and our LiDAR, we collect imagery at 10 hertz. And in some cases having stationary imagery where you might take the camera data going down the road north and then take it again going south and not take it simultaneously, that might be fine for certain algorithm development. But in our case, you know, if you're doing some safety things, it's obviously of concern to you if a car is approaching you rapidly from behind, and you can infer it's probably going to pass you and cut in front, and that might impact you know, your blind spot or your ability to do collision mitigation by braking or whatever. So I think it's important to get everything 360 degrees and simultaneous. And it's extremely important, as John mentioned, if you put public data sets out there, that you also provide the calibration for your cameras. People have to know how to unravel what went into stitching together the images in the camera. They have to know the coordinate offsets between all of the different cameras. They have to know the pitch roll yaw of the vehicle, you know, the things that come from the inertial navigation system. It's got to be very accurately time-stamped and in the same coordinate frame. And once you do that, the power in the data fusion is enormous. I showed an algorithm where we can localize with LiDAR alone and an algorithm where we can do camera alone across different seasons. But the most powerful one is when you use them simultaneously, because then that gets far more robust.
John, anything to add to that?
Sorry, I just want to echo those comments on calibration. I just can't overstate how important it is to have calibration. And LiDAR alone is not enough. You need video with the LiDAR, I think, to be able to see with human eyes inspecting the data what's happening at a given place in the road.
So Ray, there's an example of your marching orders.
Well, let me just say that when I started out on building the vehicle that was going to do the Utah collection, it was a little bit different. And then Utah has been very generous in sharing what the guidelines are for what we're going to be doing. And a lot of other different entities are getting involved. That's why we're even doing this seminar today, or webinar today, is because this data is going to have uses at a lot of different levels. And Utah, again, is going to be very generous in allowing this data to be used outside of just their DOT uses. So we've been changing some of the sensor packages on the vehicle to be easier for people who want to use the data after the fact. The data will be formatting, and there'll be a result that's produced for Utah. But the data is being collected for the purposes of this Department of Transportation, which, because the money is federal money coming in, or majority of it is coming in, it becomes kind of public domain data. So we've been looking at ways to try to set up the data itself so that it can be used, whether it's the LiDAR piece or the imagery piece or just the raw data coming in from it. So I know the university, I think University of Utah is going to be analyzing our retro data because they're working on some projects of their own. We know that Esri and Bentley and Autodesk are also going to be looking at the data to see what they can do to tweak their software environments to be able to use data like this better. It's a known fact that when you start using LiDAR files like this and some of the other things, the large images and stuff, that it can choke down a standard GIS environment or modeling environment. So we're working at ways to try to reduce the data set so that it can be used in those environments. And being able to be involved in this webinar with both Jim and John has been great because we've been talking a bit about the different pieces of this, and even as we're out testing the vehicle before it runs to Utah this weekend, we are looking at the data and how we can make it even better on the back end. Jim has really hammered home the issue with we needed to get into the 360 imaging side. That's why I've signed the agreement with EarthMine. I think that's going to be a great addition to our product line and our abilities to go out and collect this data. So there's a lot of factors in here. I think people need to pay really close attention to this project. Not that it's the only project. I have many projects this summer, but this one kind of pulls it all together. And the data set is going to be contiguous. It's going to be calibrated, and there's going to be a lot of different sets that can be extracted out from it. So again, that's why Utah is being touted as something people should watch here. And those data sets will be available for experimentation or research.
Yeah, can I add one thing that I didn't add earlier than I should have? Somebody asked me about, what's way out there in the future. We presently do similar projects to what you do, where we'll drive a large amount of highway to test some system on the vehicle. And oftentimes we'll come back and we'll re-simulate what would have happened if we changed the calibration parameters on a sensor, or do we improve the robustness, get rid of false positives, whatever. We do a lot of re-simulation work based on the premise that the data is good and we understand the physics of the sensors. If you take that to the extreme, if you have a 3D map and you have the ability to take some section of the world and make a virtual 3D community, now you could also launch into that virtual community virtual cars, and you could let them interact and log billions and billions and billions of miles, finding out where some of the bugaboos and problems yet to be solved are, without actually having to drive all of that. That's a little bit in the future because we don't have great physics models for all the sensors, and we don't have super high resolution maps of things. But in the computer-aided engineering world, that's kind of a goal to be held up, and if we do the mapping right, it leads in that direction.
And I just want to add one more thing.
Okay, go ahead.
Just one more thing is the data set we're collecting for Utah. This is an eye-opener. This is what's potentially possible. We will continue to improve it. We know it's not going to be perfect, but it's something to start with. And as the years progress, this is a multi-year project with Utah. Other states are starting to sign on. You're going to see some stuff coming from other people we're working with. We'll continue to refine this. And that's why I got involved with GTMA and feel it's important, is that we need to continue to forward this so that we can solve other problems.
Okay, I'm afraid we're over on time, so I'd like to thank our presenters, Ray, Jim, and John. For more information on any additional questions you may have, or more on GTMA, or more on the Vehicle Basemap Subcommittee, please visit www.usgtma.org. And this webinar will be posted up on the GTMA website, and it will be available for viewing in the future for those who register on the website. Thank you very much, and have a good weekend. Bye-bye.